Now, what is remaining in this part? Actually, remaining is a site. Okay, so this chart that tell us that when the wind come, there is a cut in speed, and then the power will increase until you hit, we call this the rated speed, and the corresponding power is the rated power, and that's what they put on the sticker, and they say we are selling 7.5 megawatt turbine. Why? Because that's the rated power. So the question is, when will the turbine that I spend like $10 million to buy it, when will this actually happen? When will this turbine deliver 7.5 kilowatt for me? Only when the wind is 16 meter and above, and actually not above. If it hit 25 or higher, I will not get power, because that is called the cutout speed. The wind is just too strong for the turbine, they will shut it down at that point. Okay, so the wind will be in the window, the optimum window, only between 16 meter per second and 25 meter per second. Okay, so out of the, how many hours do we have per year? How many hours do we have per year? Anyone? You guys know how many hours we have per year? 8,760. 8,760 hour per year. Okay, so you cannot forget this number, 8,760. Okay, so if the wind is in that window, 8,760 hour, per year, you are amazing engineer. You pick the right turbine for the right size, okay? Because that turbine will always run at the rated power. And if you would like to figure out, so how many kilowatt hour I'm gonna generate, because you're gonna sell the energy in kilowatt hour, right? You don't sell the energy for per watt, you sell it per kilowatt hour. So a turbine like this, sitting in a site that's ideal for it, meaning the wind is always between those two walls, the rated speed and the cutout speed. How many kilowatt hour are we gonna generate?
7,500.
Let me do this. Let me check on you. 7,575 times 8,760. Yeah, we're gonna generate 65, right? Megawatt hour, right? Is that correct?
How did you calculate that one, Dr. Salam?
So how do we calculate that? This is important. How we calculate the energy from the power. Okay, so how many kilowatt hour do we have when this thing is running at full load? 7,500 kilowatt. That's how much kilowatt hour it will generate. And if this thing runs for 1 hour, you will get this number, kilowatt hour. You multiply the power times the time, you get the energy. Okay, so
Yes.
if this thing runs for 1 hour, you will get 7,500 kilowatt hour. How much money is that worth? Each kilowatt hour is like 10 cents. At least we buy it like 11 cents, right? If you look at your electric bill in Tulsa, Oklahoma, we pay like 11 cents per kilowatt hour. So if we get this much kilowatt hour, every hour this turbine will give us $750 dollar. Every hour it will generate $750 for us, because this will be how much kilowatt hour, and each kilowatt hour is 10 cents. Now, if we run for the whole year is not only 1 hour, the whole year is 8,760, right? This is how much kilowatt hour per year. Okay, so how, like, divide over 10, so to figure out how much dollar is this, and it is $6 million per year, right?
Assume wind speed's constant throughout the whole year.
Not constant, but at least At least what? Huh? The wind doesn't have to be constant throughout the year. The wind has to be, well,
This problem would be
At least 15.
between 15 and 25.
between 15 and 25. Anything less than 15, we are not going to generate that kind of power. We will generate a little bit less, right? And anything above 25, we are not going to generate anything. It will be zero. So if the winds stay between the rated speed and the cutout speed, that's pretty easy. It will always generate this much, and you can calculate the energy out of it. And that is, if this is the case, there's something called the capacity factor. How much of the installed capacity you are using? That would be 100% capacity factor, because the turbine is always running and generating maximum load. Now, what if the year, and let's imagine this weird scenario where the year, half of the year, half of the year we are in that range, and the other half we are less than the cut in even. So half of the year you are in this ideal scenario, and the other half you are less than the input power. The capacity factor would be 0.5, right? It will be as if the wind is running only half the year at full load and the other half nothing. So now our job in the next section is to figure out a turbine like this installed in a site. So the site will have different wind speeds, and those wind speed will come at different hour period, like this. Look at this guy. So a site like this, here are the velocity that he's measuring. Between 0 and 1, 200, 0, 80 hour per year. 0 to 1, 200 hour per year. 13 to 14, 60 hour per year. Above 14, 2 hour per year. Okay, when you add all those hours, hopefully you will get 8,760. So now with a map like, or like a site like this, how much power you'll be able to get? How much, not power, how much energy you're gonna get from a place like this? What do you do? So the manual method is to basically tell yourself, okay, 0 to 1, I'm gonna write power over here. How much power am I gonna get? 0. For this guy that we just visited, where he had a cut in of 0, 1, 2, 3. Let's call the cut in speed 3. Anything that's less than 3, we are gonna get 0 power, right? 0 power, and therefore 0 energy. And when it comes to, say, 13 to 14, that is the rated power. Let's imagine for a moment here that, I mean, obviously this is the best turbine for that site because it's not as strong. But let's imagine that the rated power is at, say, 13. So you will come to the pin that is when the wind is 13 to 14 and say, 60 hour per year, I'm going to have the rated wind. So for rated wind, I'm going to generate the rated power. If it's in my rated speed, then the output power would be the 7.5 megawatt. And multiplying the hour time the hour, multiplying the power times the hour, you will get the energy. So 60, now let me get my calculator. So for that particular bin, I'm gonna say, well, I have rated power, so I'm gonna generate 7,500 kilowatt for that big turbine. Multiply by how many hours I'm gonna do this? 60 hours. That's how much kilowatt hour during the year from that particular bin. How about something in the middle? How about he from 6 to 7, he had 1,000 hours sitting there. So I go to my curve like this and I say, well, 6 to 7. Here is 6 to 7. 6 to 7. How much power is that? Only 1 megawatt. That turbine, when the wind is from 6 to 7, you only generate 1 megawatt. So how much energy will come from this place or that particular wind? I say the power is 1,000 kilowatt, right? 1,000 kilowatt between 7 to 6. And he said he stayed in that pen for how long? 1,024 hours per year. Multiplying the two things together, that is the kilowatt hour generated only in that pen. And I do this for this one and this one and this one and this one, right? And then you add all those energy together, you will be able to figure out at the end of the year how many joules, or sorry, how many kilowatt hour you're gonna able to generate. Okay, and if the turbine is not running all the time at full power, that number will be less than the rated power times the 8760. And actually that ratio, the ratio between the actual kilowatt hour generated and the maximum possible. What's the maximum possible kilowatt hour generated? 8,760 multiplied by the rated power. That ratio is the capacity factor. Okay? And so a wind turbine with a bad capacity factor or a wind farm with a bad capacity factor mean, what does it mean if the capacity factor is 0.3 or 0.2? It means big mismatch. You didn't put the right turbine in the right site, right? So the turbine is oversized. That turbine shouldn't be installed in that site. Should have picked something smaller, right? Very good. So I'm gonna go back to this table again in a minute. But so if that turbine was too big, you pick something, you know, a little bit smaller, right? Something that, look at this one. This one, go to the rated power. So this is a smaller turbine, 330 kilowatt compared to 7,000, right, kilowatt. And you can see how it had the rated speed, or the rated speed is like here. It's like 12. Well, I mean, let's call it 13. So the rated speed is 13. So with a rate speed 13, that's much better with one with a rate speed 16, right? So the wind smaller, you pick this one. But if the wind is like really very strong most of the time, then this would be kind of lost opportunity, right? You can generate much bigger by going to bigger one. Okay, and we talked last time about how the CP is doing this, right? Why he's doing this? Because up to this point, he's struggling to make the CP peak. And once he get the right speed, he can get his CP to peak up, and he's peaking here at 0.5, right? And then after that point, he on purpose start to slow down the CP, or like make it worse and worse, because as the wind builds up, he does not want the turbine to generate more. Like otherwise, if he maintained that CP, the output power would look like this, right? It will look like what? Like half rho V cube. You know, have you ever seen the equation y equal x cube? It shoot all the way up to the sky, right? So it will end up shooting really high, and he doesn't want this because that will break the generator and the bearing and everything. So he screw up the turbine plate by the pitch control so that he will take his CB down and down and down, so the output power stay fixed. Although the V is, you know, what's the difference between 10 cube and 25 cube? A lot, right? Between 10 cube and 25 cube, that's the difference between 0.5 and 0.05. So he's dropping the CP from 0.5 to 0.05 because the 10 cube and the 25 cube. And for all of them, he just generated almost the same power. So what he's trying to do here in the next section is how we can do this for an actual site, you know, with bunch of data like this, you know, velocity and hour, velocity and hour. And I used to make this the project of the course. Actually, at 1 year, there was like really to design a wind turbine, like give them the site information, and the turbine characteristics, and then they will actually mesh it and pick the right turbine for a place. Okay, so this can done very quickly if you actually have the equation of the curve. What curve is this? The site curve. That's the PDF of the site, the probability distribution function. Okay, so when you look at that table and this graph, you would say that he's dividing the wind speed, bin number 1, 2, 3, 4, 5, and that corresponds to certain velocity. Okay, and for each one of them, he got a data point. Okay, the black is the data points, but it would be nice if we have a curve that describes the whole thing, a function, so that then we can use it in MATLAB or Excel and then keep optimizing our design, right? And like take this curve into the turbine curve and figure out, does this one work? Does this one work? So what is the equation for that curve? It turned out that, you know how the students' grade should be like a bell curve, a Gaussian. If everything is perfect, in a perfect world, the students should have like a distribution. Well, the wind, if everything is perfect, the wind should follow that curve. That's called the Webel distribution. Okay, and it look complicated, but it's not really. There's only two factors here, the K and the C. What's the V then? The V is the velocity, that's the x-axis. Velocity is 5, 10, 15.
Dr. Salam,
Yes.
can you please help me explaining the previous two slides, like the before slides, previous slides?
This one?
No, I think this is the slide 21, I guess.
This?
No, previous than this one. The upper graph, yeah.
This guy?
No. After this one?
I think you're talking about this.
Yes, this one. I mean,
Right. So the table, you understand the table? What
no,
does the
this
table
one,
mean?
not this one. Previous than this one.
This guy,
Yes, the upper graph. I mean, like
this one, and this one.
yes.
So those are the wind turbine characteristics. It can be represented by two graphs. This guy, and this is simply the power output as function of the wind speed.
So that basically defines, like, we don't have the, I mean, like the maximum efficiency will be like 59%, right?
So the maximum efficiency is achieved here, and it's 0.5, not 0.59. So 0.59, that's what Pitts told us is possible, but mechanically, you will not get it. There's generator, there's gears, there is like bunch of stuff that will make it not perfect.
So that means
Right?
59% is the theoretical efficiency.
The 0.5, the 59% is a theoretical, right? And no one can achieve this unless your turbine is running with on magnets or something like there. It's like magnetic bearing and superconductor coil, and there is no losses whatsoever in anything.
Okay.
So
basically we can get up to 50%.
the fact that they got to 50%, you should be super excited. I mean, this is amazing. You should actually say, wow, they actually managed to get that close. That is like pretty good, right?
Uh-huh.
So this is the CP. This is the CP. The CP is the power output over the power input. What's the power input? That velocity cube time half time rho time the area. That's the power input. So you can get this graph from those points. Just you come here and you say, what's the output power? 250. If you divide 250 by that velocity cube time half time rho time the area, how do I get the area? Well, look at the pressure of the turbine and figure out what's the area of that turbine, right? Then you will figure out, when you divide those two things, you will get the CP to be this much. I will call it 0.48 or something. Okay? So that CP is nothing but that curve divided by the input power. And that curve is read on that axis, and that CP is read on this. And it's really confusing, but when you look at the label here, power coefficient CP, that's basically this guy. Power, he should have said power output. Power output kilowatt, that's this scale, and it's that curve. How do I know that this curve go here and this curve go here? Because I know how do they look like. I mean, if I am an engineer that took that course, I know that the bar output need to look like this, and I know the CP like this. But if I'm a shag working for shag.com and I'm trying to solve this problem, I may get confused and think, that is the bar output and that is the CP. And then I will solve the problem wrong and I screw everyone else with me. Does this make sense?
Yes.
Also, there's a legend here when you think about it. See, the legend say which is the CP and which one is the power output. Okay, so this is what the turbine is doing. If you give it that velocity, that velocity, that velocity, that curve tell you immediately what you should get. So what we are trying to do right now is trying to figure out, so what is the wind in that place? And the wind will end up being a curve like this. When the majority of the year, it's like say 14% of the year, the wind stay between here. And very few hours per year, the wind stay here, and very few hours per year, the wind stay there. So manually, we can go to every bend, say how many hours, and look at the velocity and go to the turbine curve and figure out when the wind was this much, how much power does the wind generate? And you multiply the power time the hours, you get the energy. Power time hour energy, power time hour energy, power time hour energy. You add all those energy, kilowatt hour here, kilowatt hour here, kilowatt hour here, kilowatt hour here. You add all this, you get the total kilowatt hour per year. Okay? But rather than doing it like this, people like to use equation for the site. And that equation is the Weibull distribution. Okay? And that Weibull distribution, the shape of the curve is function of that K and the C. The K is called the shape factor, and it will stretch the curve or make it a little bit spiky. And the C will take the curve right or left, depending on what do you call that velocity, guys? Like, let's say that it's 8 meters per second. How do you describe that velocity? What would you call that velocity? Anyone? The velocity that corresponds to the peak of that curve, what do you call it? Is that the average velocity?
Be the maximum.
Is that the maximum velocity?
All right, yeah, that'd be the, yeah, I would say that'd be the average.
It's not the average and it's not the maximum. The maximum is this.
Tip speed?
What?
Is it the tip speed?
No, the tip speed have nothing to do with the wind. It have something to do with the wind. The tip speed ratio is the wind speed multiplied by the tip speed ratio that you would like to use, like in our homework. The wind is at 14, I multiply by it want to run at 8 times the wind, so that would be the tip speed. No, this one is, see, this is the maximum. Do you realize why this is the maximum? Because this graph is the probability of each one of those speeds. Huh? This graph, this HV is how many hours per year did you stay here? How many hours did you stay here? How many hours did you stay here? And so the maximum in that site is this. So this is like, say, I would say 25 meters per second. This point is like maybe 1 hour per year, the wind hit 25. That's when tornado was blowing by and we registered 25 meters per second. But this one would be
The probability, I mean like probable velocity or speed.
yes, I would call this the most probable speed. And from statistics point of view, you call this also the mood. That's the mood of the curve. You hear sometimes some distribution called bimodal when they have two peaks, like you go up and then you go up again. That's called bimodal. but that is the mood. And so why it's not the average? Why the point where he peak up like this is not the average?
Well, I guess it's not necessarily what it's at most of the time, or what.
See, this is what is most of the time. I mean, it's not as spiky as you wish, but if this speed, the corresponding to the tip, that is most of the time. Like if I'm gonna pick a turbine for that side, I will try to make it work here, maybe, because that is what is the wind is most of the time. All right, but the why this is not the average? Because the curve is not symmetric. The curve is not symmetric. If the curve was symmetric, the mode become the average. That's why in Gaussian distribution, the mode and the average are the same. It's the point where the curve go up to the top. That is the average and the mode. But in this distribution, this is the mode. That's the most frequent velocity, but the average will be a little bit to the right or to the left. It's gonna be a little bit to the right because of the long tail. It's gonna be pushed a little bit, right? Now, those guys, now, if I'm gonna pick a wind turbine for that site, should I really make it work only over here or work a little bit over here? So those velocity, what's wrong about them is that, what's wrong about them? Why we shouldn't buy the turbine just to run between 15 and 20? Why that would be a total loss of our money?
It's not going to be reaching that as often as the other ones.
It's not going to be there most of the time, right? This is going to be there like maybe 1 month per year, because look at the number of hours. However, also it's not smart just to ignore totally everything above the mood. Why? Because even this part, even the fact that they are not as frequent, it's only like say 4 months where they would stay here, but the fact that they are so high, that can generate a lot of money for you in this place. Why I'm saying this? Because the energy, it depends on the power, it's time multiplied by power. And the power scale with V cube. So when you go from 8 to 12, it's a big deal. 12 cube and 8 cube. Big deal between those two guys. So that's why you need this kind of analysis that we're gonna do next. He need to be able to say, I actually want to calculate exactly how much energy is going to be generated if I have this turbine or that turbine or this turbine. Then he will transfer all this calculation into, actually, here's how much dollar it will actually give me. Okay, this is just trying to show you how, like in this curve, if you make K change, it will make the curve go from K3, look how spiky it is, and almost like Gaussian, to K2 with a really long, a little bit tail, to K1, which is, and then he will tell you that most wind sites actually have K equal almost 2. So that is like the site, the shape that we have. Okay, C will take you from 10, like when C, by the way, C has the units of velocity. So whatever the unit of velocity meter per second, C also will be meter per second. But K does not have a units. It's just like a factor. Okay. So here's what the C is doing. So when C get bigger, the curve move to the right, move to higher and higher velocity. So then a site like Tulsa, Oklahoma, or the Panhandle of Oklahoma can be characterized by a K and a C. And then you will have the whole year. If this was a good fit, you can see the whole year represented by a graph. Then you would couple this curve with the turbine, and you'll be able to generate or figure out how much kilowatt hour per year is coming. Okay, why? Because this curve tells you exactly how much hour per year for every velocity you got, right? That's basically what we want. You want to multiply those hour. So at 5 meters per second, you figure out how much hour there is, and you multiply this by the power of the turbine when the wind is 5 meters per second. Then you do it at 10 meters per second. How many hours there is? 500. What was the turbine power when I'm running at 10? And so that's 2 multiplication will give you the kilowatt hour. Okay, he will have an example for us to see. But as I said earlier, most wind turbines, or not most wind sites run at K equal 2. Or like K equal 2 is pretty good approximation. So that's why there's a whole curve called, rather than Weibull distribution, it's called Rayleigh distribution. And when you look at the Rayleigh distribution, it's exactly Weibull distribution, but with K equal 2. So the Rayleigh distribution have only one parameter because he got his K fixed at 2. So they realized that rather than just like keep wondering what is the K is, let's just make K equal 2 and just find out what is the best fit for it. Okay. So the Rayleigh distribution, because it has only one variable, it's very easy to write it in terms of U average, and that's it. All you need is U average for the site, and you will be able to calculate the distribution. Is it as accurate as Weibull? No, Weibull is more accurate because you have 2 knobs and you can really fit the data perfectly, right? But Rayleigh is pretty quick to come up with because all you need to know, what is the average site in the Panhandle in Oklahoma? 14 meters per second, with 14 meters per second, I got my distribution. Now let's see how much this turbine will generate for us. Okay, so now when you have the distribution, whether it's like this guy, f of x, or it's this guy in that shape, at the end of the day, it's bunch of number multiplied by velocity, the x-axis. Make sense? So now what do you do with something like this distribution? You can calculate the average from it, of course, by doing this. So this is not just the wind, this is anything in statistics. If you have the distribution function, h of v, that shape, that graph, the equation that relate that the probability back to the velocity, and that distribution is e to power v square, or square root of v multiplied by sine v, whatever the shape of the distribution. If you want the average, you multiply that function time v, and you integrate from 0 to infinity. Of course, we panic whenever we see integration, but we shouldn't, because the integration, it turned to be summation when you have like bunch of tables or bunch of values, discrete distribution, right? But if you have the continuous function, you just multiply by v and you integrate. And from 0 to infinity, don't panic from infinity. Basically, what will happen is that you'll integrate up to like, for this guy, you integrate up to 40, and after that, it's 0. Nothing is coming. And anything that's coming is like trash, basically. Very little. So you don't worry about it. Okay, point is, you can calculate the average velocity from this. Okay, and interesting, the average power available, how do you get the average power? Again, the distribution function of V. This is important. It's not the distribution function of the power, it's still the distribution function of V. So that curve give you the average velocity, give you the average power. How do you get the average power? Half rho V cube time h of V. Again, this is like numbers time V. 4 multiplied by V squared to e to minus V. You multiply by this and you integrate, it will give you the average power. So can't I get the average power by saying that it's half rho V mean cube? Can I do that and say that's the average power? So he's dividing by the area, by the way. So power per area is half rho. Can I use V mean cube? If I have the average velocity in the site, doesn't that mean that the average power is half rho V mean cube? And the answer is No. The answer is no. So that is weird. But you will see this a lot in fluid mechanics. The average of the square, for example, of V cube is not the square of the average. Okay? And the same thing for the cube. The average V cube, so V cube, if I want to figure out what's the average V cube, I want to put a bar over V cube and I want to get the average. That's what we are doing over here, by the way. We're trying to get the average of V cube. This is not the cube of this. Okay? So he's saying that if you want to get the average power, you really need to do this integration. You need to do HVV cube and get the average. That would be the average V cube. And if that velocity, if you want to take the cubic root of this would be VRMC or something. This is the velocity that when you cube it will give you the average power, but it's not V mean cube. Make sense? All right. So now he's saying, assuming a perfect CP, huh? Not like Spitz perfect CB, but like 0.5, like the one that we saw here. That was 0.5, right? They could do it. It's not that hard to do 0.5, right? See in this map, 0.5 is doable. So assuming CB 0.5, which is not far-fetched at all, then if this is what's available in the wind, you multiply this by half, and so it will be half times half, it will be 1/4. This would be the actual power output from the turbine at the rated speed, right? And so then you can find out what is the maximum possible energy from that site, assuming that the turbine will always run at 0.5, and you'll be able to calculate the energy. How did you do the energy? The power, V cube, multiplied by the hour, the 8,760 hour per year. So this will give you the energy extracted. Hours multiplied by the velocity. Okay? Does this make sense? Notice that the HV is the distribution. You multiply it by this, and it's those two guys together is a fraction of the 8,760. Because HV was how much percentage of the year do I get V? That's the definition of the probability distribution function. It's the fraction of the time I stay in that small range. Okay? So here is the example. He say, I got that distribution. Okay?
Dr. Salam.
Yes.
So in all these cases, we are assuming gearbox efficiency and the electric generator efficiency to be 100%. Is that correct?
You are, so again, if the CP, it depends on what is your definition of the CP. So if you think the CP is the overall CP, not just the aerodynamic CP, then all those small guys will be embedded inside. But if we are looking at a chart like those one that we have seen at the beginning of the thing, those are aerodynamic one. Make sense? So when you are looking at something like this, he's giving you all the specs on the thing. That CP is the actual power in kilowatt, the actual electric power, not mechanical power, not shaft power. Does this make sense?
Not really.
I'll tell you what, you have the right to know, when someone as a student or like you are actually working as an engineer and someone send you a number, you don't have to wonder about it. You have the right to ask him, what is that number? How is it defined? If someone tell you, well, the efficiency of the gearbox is this much, you need to tell him, is that power output over power input? Is it mechanical power output of mechanical power input? So in the same sense, when someone give you a CP, like in this example over here, you need to say, is it electric over aerodynamic or is it mechanical over aerodynamic? Did you include the generator and the gearbox in it or not? Okay.
So when there comes the case of mechanical, then there will comes the gearbox efficiency and the electric generator efficiency.
Yes, because
Ah,
so the wind go into mechanical energy through the rotor, but then the mechanical energy turn into electric energy through the gearbox and the generator, right?
mhm.
Very good.
Okay, thank you.
Yeah, but look at there is more problem than what is CP than this. You should have asked me about that. CP is 0.5 forever. Like, how is that possible? What is that turbine that have 0.5 all the time? That doesn't happen, right? Did we see? We just saw that how the CP is going doing this, right? How is it possible that CP is 0.5 from 0 to infinity? For all those velocity, you have one constant CP. How is that possible? Not possible, right? Not possible. But this is just an example where if we know the CP, we can do this. Ideally, you should actually know the CP as function of velocity too. So you don't just throw half over here. No, you throw a function of V in here. Make sense? The CB is function of velocity for any particular turbine. You agree? Look at it. You see how the CB is function of velocity? All right. So in this example in our book, he say, if I have a site like this, and that site, you can get that graph if you make K equal 1.5 and C 15 in that equation, the Weibull distribution. Okay. So turbine running at a Weibull distribution with C 15 meter per second and K 1.5. Find out the V mood, that's the mood. The V mean, we need to do the integration of HV times V and the VRMC. That's the V cube, the average of V cube. And so he will do this with that integration. He gets 13.5. He do this, he get 18.9. And you see how they are different. And you will see how that velocity for the RMC is always a little bit on the higher side. So the average velocity, 13, but the power, the average power come at a bigger velocity range. So maybe the turbine need to be sized with this rather than this. But it's not just one velocity. Again, it's a match between the two of them. So this graph is the energy. He got that by having CBE 0.5 all the time. Again, it's a big F, right? But that would be the graph for the energy. How 8760 times the half rho V cube. That's basically this equation that he's integrating. Half rho HV V cube 8760. What's the point? Why I'm showing you this? Because look at the energy, look at the velocity and how those guys have almost no hours on them. No hours, very little hours. From 0 to 15 to 20, most of the thing, and from 20 to here, nothing. 20 to 50, nothing. But here, you look at 20 to 50, and wow, a lot of energy in that place. Energy mean kilowatt hour, which mean divide over 10, and you will see your dollars. This is where your dollars are. Okay, so even the fact that they from 20 to 50, you look to this and say, I don't get hours here, most of my hour over here, but my dollars, my energy, my kilowatt hour, 20 to 50 is here, right? So if you want to get all the dollars flying in the air on top of you, you need to make your turbine run in that range, not this range. Because yes, this is a lot of hour, but no power. I mean, imagine if the site have almost zero wind most of the year and like 1 month when the wind blow at 10 meters per second. So you get a turbine that run at zero wind because that's most of the wind? No, you go for the place where you have the joules. Okay, very good. But now the CP.5 is making this site, huh? Giving too much credit for this part. Why? Because it's assuming that the turbine would run all over the place with 0.5. We actually know that once you hit V rated, if we get a turbine that's rated to 25 meter per second, from this point on, what will happen? The CB will drop, right? Because he will have to maintain the rated power. So we need a good equation for the CP, right? Right? So this is, he's trying to explain to us why the CB will drop. It will drop because we will control, with all this controller, we will control the pitch of the airfoil. So rather than perfectly aligned with V relative, huh? We said the plate need to be perfectly aligned with V relative. We will end up screwing him. We will end up making him stalled a little bit, so that once he hit V rated, he will start going down energy wise. And once he hit the cutout speed, he will completely stop, right? So he's saying that the wind as function of time could be something like this. You see how much it will vary? But the power output should be like this. The turbine should deliver, like he's saying, this is like 900 kilowatt turbine, 850, okay, 850 kilowatt turbine, almost 1 giga. Sorry, always 1 megawatt turbine. So the power output should always be like this. Okay, so how that will happen? Well, first of all, you need to change the RPM with the wind. You make the torque a little bit lower or stronger so that you maintain that tip speed ratio. And look at the angle of the plate. So he's continuously changing the angle so that he maintain the power output the same. Make sense? So there is active control all the time. So as a result, he's saying that with a CB that's always half, again, this is the bar input, half rho AV cube, right? You just get half of what's available in the wind. But in reality, once the turbine hit the V rated, it will be constant and then stopped after that. So this part is controlled CP, a CP that drop, so that the V rated never hit more than this number. Okay, so the ideal CP would be something like this. We know that the real CP will actually not look exactly like this, right? We saw the real CP. You see how it's doing that? But he's saying, well, the ideal CP should stay at the maximum, and then just go down. With this part, we know that once he will hit the maximum over here, and then he need to drop. But assuming something like this, how does this kind of ideal CP, rather than just 0.5 all the time, how will it control or change the energy output? So that's easy. From here to here, we have a linear relation with the velocity, and here just constant number, and after that is 0. Right? So in this example, he's saying the wind output, the power output, the rated generator is 7.5 kilowatt per meter square. So the energy per unit area is capped at this number. And the maximum CP is 0.5, which will be here at this point. And after that, it will drop from us. Okay. Determine and plot both the system with no control and the system controlled. So, and this is the last, this is the best part of this problem. The total energy extracted by the system. how with something like this will you be able to calculate how much energy is coming out? Okay, and he's solving the same distribution that we had before. Okay, so the problem that we solved over here, this guy, huh? How much it will look like if we have a controlled CP. And so that would be the controlled CP. From here to here, you are 0.5, and then after this point, you go to 0. And from here to here, you have to maintain the V rated. So it will be like this. Okay. So now with this CP in the equation, you will find out that the equation, rather than being like this, that the graph that we showed, this is the energy extracted. Now it will look like this. So from this part, nothing happened to this part. Up to this point, we are assuming constant CB of 0.5. But from this point to here, from V rated to V cut out, you go like this. And after 35, 0 power output. So without control, you would think, I can run my turbine during tornadoes. Like that would be a lot of energy. That will give us, but in reality, no, there's a V rated out. And so this graph, this cutting of the graph is because of the site and the turbine. So this is the statistics of the site. This is what energy is available in that place. And this when the turbine come and say, no, you are not going to run after that place. And so you as someone who's selecting the turbine, you are actually controlling where does this curve come. You are choosing the knife that you'll chop at, and realizing that if you go higher, I mean, the easy solution would say, well, why don't I capture everything? Let me just go all the way up till here. What's the problem of getting a turbine that run all the way to 50 meters per second? What's the problem? Why do we have to shut down at 35? Let's shut at 45 and get more.
That can be a lot.
Energy.
It will be expensive. That turbine, the one that will go to really, really high velocity, is probably going to be very expensive. You're going to buy a Hummer in form of a turbine, basically, to take that wind. So it's not that easy choice. This will cost money to go higher than this, right? And also because that part, when the CB remain 0.5, that's also a little bit fictitious because we just saw that the CB climb up. So by going a little bit to the right, you are also going to lose some of those guys. But at the end of the day, a graph like this, where you chop the energy available, first of all, I would love for you to be able to generate that curve. Okay, the energy available in the wind. That is like, just by this curve is like, you can learn a lot. You can see how much joules are available, and then we can choose to chop. At our level, we can just say what is V rated and what's the out and what's the VN. That would be an easy choice, at least. V rated, cut out, and say the cut in would be like this. Okay, so one I know we are running out of time and we should take our restroom break right now. So let's take a 10 minutes restroom break and we'll start again at 9.
So Dr. Salam, before taking a break, I just want to ask you one question.
Yeah.
So
Everyone, go to the restroom. Leave Bevan. You can go. You guys can leave. Okay, so ask your question.
Yeah. So why is the exit velocity in the wind turbine cannot be 0?
Yes, let's answer this after they come back from the break. That's a very good
Okay.
question. Yes.
Okay. Thank you.
All right, I think we should start again. So can you guys confirm you can hear me?
Yes.
All right. So the question before the break was that free homework problem that I asked it for last week, which was, what's the answer for it? The question was why Beth said that the efficiency of a wind turbine cannot hit more than 59%. And in the case of the hydraulic turbine that we saw last week, the week before last week, that Belton wheel was 100% power efficiency possible, theoretically possible 100%. And that graph that have Francis and Kaplan, they were all like 90 and 85. So the question was not why, the question was not why the wind turbine cannot hit more than 59. That was his work. He showed to us why. The wind turbine cannot hit more than 59 because the wind has to go through. If you hit 100%, the wind will not go through, and the power output will be zero and efficiency will be zero, or the CB would be zero. So we understand why it has to be less than 59. What was the question was, and what we don't understand is, so now why the Belton can do 100%? Why the Kaplan can do 88%? Why the Francis was doing 90%? How is that possible? Don't they still need to go through as well? And if I slow them to zero velocity, that is the meaning of 100% efficiency. They leave with zero velocity. If they leave with zero velocity, wouldn't that mean, just like the wind, that they will not go and the power output would be zero? And the answer is no, they still can leave. In case of the water, even with zero velocity, they can leave. How is that possible? How does the water leave if it's zero velocity? Here is my exit pipe, okay, of the turbine. And if I'm gonna open this, I don't wanna get wet, but imagine if I open this and the water is with zero velocity, will it drop or not? It will drop. How is it dropping? It's like zero velocity. Why it's going down? Why it's leaving my exit? Because of gravity, because it still has potential energy. But the wind leaving the turbine doesn't have potential energy to drop to, okay? And that's why I told you that the turbine that I showed you in Facebook, the one that they're gonna put it in the current, which look like a helical wind turbine, that one will follow a bit slow. Why? Because it's immersed in the water. So the water still need to go through. There is no way to drop from the back. It need to go, and it need to leave with that velocity it's coming with, right? So again, the people in Tunisia that said they have a wind turbine that's running at more than bit slow, the thing that you should always think, is that possible? You need to tell yourself, can they leave with zero velocity if they want to hit more than 59%? And yes, in their scenario, they have like a wobbling disk that keep doing this. And again, I didn't really look at the exact design, but in that scenario, if the disk is keep doing this, then you can imagine that as he bounce or wobble like this, he is sending the wind out, like he's scavenging them out of the way, right? So there is a chance they can get more than 59% because it's not going through. It's not like you need to let me leave. No, you can go up or down or right or left. Okay? Does this answer the question? So I didn't really read all the answer. I only read one guy, and he answered in the wrong way, meaning that he was explaining why the wind will not go. I know that part was easy. And I told him, no, the question is, why is the water is getting more than bit slow? Not why the wind is getting less than bit slow. Okay? But I'm gonna read the rest of you guys. If anyone got it right, I will tell him that he has a free homework problem. Okay, two more things I wanna talk about before we leave this chapter. In a wind farm like this, it's also important to space them right, because if you stack them very close to each other, there is a wake. Remember, we said there is a swirl that will come behind, and that wake, not just because of the swirl, it's also because it has reduced velocity. So you need time until the air basically build that flow again, right? So you cannot just put them immediately after each other. So they say 8 diameter, 8 to 12 diameter away. And to other extent also, if we have a wind farm in the Panhandle, how far can they put a big wind farm in Kansas? Because a big wind farm will probably take the energy out, and it takes some distance before you can put another one. So there is concern about this as well, right? The second thing that I wanna finish with is why do they build them so high? And they build them so high not just because the diameter is big and it need to go high, huh? I mean, look at this. I mean, doesn't why this guy could have been here, for example. Why do they go up a little bit more? Why do you think this is the case?
They're able to streamline better and not as turbulent, I would assume.
The velocity is higher, huh? Let alone the turbulence. Yes, there could be turbulence from the building and stuff, but also the velocity is higher. So there is a boundary layer, atmospheric boundary layer. So the velocity is 0 at the floor, and then it go up, increase. It increases with the height. Okay, and that is the equation. U at U reference, say 50 meter per second, is Z over Z reference. So if you're gonna put it at 100 compared to 50, the velocity at 100 compared to the velocity at 50 would scale with Z over Z reference to a power alpha. What that alpha? That alpha is the ground effect. It will wind shear coefficient. So they will tell you if you are a flat surface, like say offshore wind farm where the ocean has a flat surface, alpha would be really good. But if you are installing this in the middle of a cornfield, maybe the alpha would be a little bit less. If you are into an urban area, like a little bit of suburban where there's a bunch of houses, 2 floor, 1 floor, 2 floor, that alpha will be different. Okay. So how is that going to be useful for us? If you have a table like this with wind speed an hour, wind speed an hour, and that was done at 30 meters. This table was done at 30 meters. And you're going to buy a turbine that is sitting at 50 meters. How does this table will look like at 50 meters? What should we do? So they measured this as 30 meters, I guess, with a stick sitting in the airport, and they got the velocity. Velocity 6 to 7, 1,000 hours per week. 7 to 8, 700 hours per week. That was at 30 meters. What would be that table look like? What does this table look like at 50 meters, where we are planning to put our turbine? What should I do? Should I change the hour, or should I change the velocity?
Probably change the velocity.
We changing the velocity. The hour remained the same, meaning that when it was at 30 meters, 6 to 7, and that happened 1,000 hours per year, well, that 1,000 hours per year will stay the same, but at a higher velocity at the higher elevation. Okay, so how do I get the corresponding velocity? I do 6 to 7. What is that? 6 to 7, that would be like 6.5. So 6.5 here, 30 meters here, 50 meters here, alpha, depending on the train that I am sitting in. If it's a flat surface, 0.2. So 0.2, 50 over 30 multiplied by the velocity at 30. So 6.5, I will calculate the new velocity. It will be higher, and that velocity will replace that line over here. So that 1,000 hour will belong to a higher velocity at the higher elevation. Okay? That is pretty common in those problems, because like when you get this problem in the exam or the homework or something, because that table will be usually at one height, and usually the turbine is completely a different height. So you need to be able to move the table to their height. Okay. Very good. So that's all I want to say about wind energy for now. And I want to switch to solar. So I guess one more graph. Let's look at this graph too. This is not just wind. This is any renewable energy source. This graph saying that when you install the turbine in year zero, you have to pay, I don't know, $30 million. $30 million day one. Why? Need to get the contractor, you need to buy the equipment, you need to install. $30 million from the bank into the contractor and the manufacturer and supplier, and you will start getting money every year. How much money you get? The 8,760 hour time the rated power time the capacity factor. How much hours per year, what fraction of the hour per year does the turbine run at full load? I have a turbine that will run at capacity factor 0.5. So 0.5 multiplied by the 8,760 hour time the rated power, that's the kilowatt hour generated, time 10 cents, that's the dollar per year. So the dollar per year will make a dent in my debt of $30 million. Second year, I get a little bit more. Fourth, fifth, sixth, you will get your $30 million by say year 9 or 10. And then after year, now you are breaking even after year 10, then you will start making money. So what that tell us? It tells us that all those renewable energy require serious investment. So if I want to put a solar panels on my house right now, I have to pay the $10,000 immediately. And once I cover my ceiling with like $10,000 worth of solar panel, then I would hope that this thing will survive for solar panel, survive say 7 years without any hail damage, without any problem for 7 years. And then after 7 years, I'll get back my $10,000. And then in the year 8, I will start make profit. And year 9, if I'm still alive, I'll get more profit. And year 10, my sons will make the money. So it takes initial investment, and you get your money basically year by year. Okay. And why the 3 different curve? He's saying, well, what if it's not your money? What if you are actually borrowing it from a bank? Then not only you have to return the $30 million, you have to return the interest rate too. So it takes even longer, depending on the interest rate of your loan, if it's not your money, right? So it will take you, say, 16 years to break even. Okay, so that is the nature of renewable energy that require big equipment and investment. Yes, fuel is for free, and that's why every electricity that you're generating is income, but you have original debt that you have to deal with. Questions? All right. So now let's move to solar energy. Chapter 6.